To find the peak of traditional physics-based robotics, you look at Boston Dynamics Atlas. It weighs 89 kilograms and features 50 degrees of freedom, the 50 independent joints that allow it to spin and jump. But at over $150,000, Atlas is a research benchmark, not a tool for everyday labor. Tesla's Optimus starts from a different premise. It's designed as a data-first machine, built to bypass the need for manually calculated physics. Optimus has a 57-kilogram frame and a target price under $30,000. It doesn't rely on hard-coded equations. Instead, it uses an end-to-end neural network, a computing system that learns to connect visual data directly to motor torque. Manually coding every joint movement is proving too expensive and rigid for mass production. When a single robot has to navigate the unpredictable human world, the old physics-based models struggle to scale. This chart shows how the shift toward AI software is impacting the market. Projections show the robotics industry growing to $124.77 billion by 2030. We can see the scale of this growth in the current numbers. There are already 4.2 million industrial robots active globally. Amazon alone operates over 1 million warehouse robots. These aren't isolated machines. They are coordinated by an AI model called Deep Fleet. The industry is moving away from the isolated, scripted robot and toward these large-scale autonomous workforces. But there is a flaw in using a standard large language model to run a robot. The AI understands human words, but it doesn't understand physical reality, often leading it to suggest impossible actions. Researchers solved this using SeiCan, a method grounding language models by checking the physical environment before planning. SeiCan scores specific skills, like find apple or pick up apple, based on physical affordances. It calculates the mathematical probability of a skill succeeding in that specific room. For complex tasks, engineers use chain-of-thought reasoning. The robot is forced to generate an internal explanation, deducing, for example, that a spilled drink means it must first find a sponge. Through these grounding frameworks, prompt engineering becomes the decision-making layer of the robot, turning an abstract chatbot into a logical physical agent. But how do those high-level text commands actually become fluid movement? The core of this is the Vision Language Action Model, or VLA. This architecture maps visual data and language directly to robotic joint movements. Older VLAs were rigid, but new diffusion networks allow for continuous motor control. The robot can now adjust its movements 50 times every second. NVIDIA's GROOT-N1 model uses a dual system approach. It splits the work between a slow, logical brain for planning and a fast spine for physical reflexes. Standard AI models are often too heavy for robot hardware. Engineers use efficient linear models like RoboMamba to shrink the parameter count, the number of variables the model must process, so the AI can fit on onboard chips. By separating reasoning from physical reflexes, engineers have successfully put massive AI capabilities into affordable, real-time robot bodies. We are seeing these software models transition from labs to heavy industry, such as the BMW plant in South Carolina. The Figure 02 humanoid, powered by a vision language model, is already performing industrial tasks 4 times faster than previous non-AI iterations. This incredible level of precision is even moving into the surgical operating room. Researchers at Johns Hopkins taught a Da Vinci surgical system to suture wounds autonomously using imitation learning, a process where the robot learns by watching human demonstrations. By watching 20 hours of surgical video, the robot reached the skill level of a human doctor without any hand-coded programming. Robots are moving away from manual physics code. They are now acquiring complex physical skills by processing human data. The shift from rigid, single-purpose scripting toward generalized AI is accelerating. The future is the RESER framework, the reduced instruction set robot. Here, the hardware relies on dynamic, generalized movements rather than unique, bespoke scripts for every task. Large language models are becoming the high-level reasoning layer for hardware. They can now string together basic skills to navigate the chaotic, unpredictable environments built for humans.